Hi, I'm Yishun Wang from University of Michigan, and I'm presenting this work on tracking deformable objects. The motivation of this work is straightforward. We would like to track deformable objects like ropes and cloth for later manipulation tasks. However, existing works are hard to conform to motion constraints and deal with significant occlusions. In addition, when self-intersection and obstacle interaction happen, they are hard to enforce geometric constraints. As you can see from the result below, which is from CDCPD, when tracking the rope winding around the cylinder, the tracking results could penetrate the cylinder and result in inaccurate tracking. I will follow this outline for the rest of my presentation. I will talk about the background next, and then methods and results. At last, I will talk about conclusion. Deformable object tracking has been started in computer vision community. However, they don't have an explicit model for deformable objects, which poses difficulty of using it in manipulation tasks. Because in manipulation tasks, you generally need a fixed size configuration of objects. As you can see from the right bottom figure, this is the result from dynamic diffusion by Newcomb. Also, to deal with self-occlusion for deformable objects, some work requires features on deformable objects. It's not realistic in manipulation tasks. In image-guided surgery, some researchers worked on deformable object tracking, such as tissues. However, it needs textural features or high-fidelity simulation. It's not realistic in robotic manipulation too. There are many works on deformable object tracking in robotics community. However, they are mainly restricted to specific kinds of deformable objects or specific tasks. They are hard to generalize to unknown deformable objects. In summary, many existing works on deformable object tracking are not suitable for downstream manipulation tasks. The most related works are Shulman's work, which is based on GMM and CPD. There are several works developed from that. We focus on CPD plus 6 and CDCPD in our work. CPD plus 6 incorporates physical simulation for better handling self-occlusion during tracking. However, physical simulator could need a lot of parameter tuning. CDCPD deals with occlusion without physical simulator. But self-intersection and obstacle interaction are not taken into consideration. In addition, it could still fail on significant occlusion. I will talk about methods next. First, I would like to talk about Gaussian mixture model, which is the framework of our method. Then I would like to introduce 3 regularization terms we added in GMM framework. At last, I will talk about posterior constraints. Here is the framework of our method. We assume that the initial configuration is given. Then the masked point cloud of the deformable object D and the previous object configuration are input to GMM module. After that, the posterior constraints will hard constrain GMM result so that we could obtain the final result P. In GMM, there are 3 regularization terms. The first 2 come from previous works, and the third one, the blue one, is what we proposed. It's used to handle significant occlusions. There are 4 constraints in posterior constraints, and similarly, the first 2 come from previous works. The red blue ones are what we proposed. They are used to deal with self-intersection and obstacle interaction respectively. We frame deformable object tracking problem as a GMM problem. In other words, we represent the deformable object as a Gaussian mixture model. P is a set of Gaussian center, and PM is the element of P. E here represents edges connecting those points. We assume that the point cloud we observe is generated by the underlying Gaussian mixture distribution P. We also assume that the initial configuration is known. Therefore, tracking the deformable object problem is converted to a point registration problem. We would like to align previous object configuration to current observation by maximizing likelihood of D. It could be realized through looping between expectation step and maximization step. In each step, we calculate the expectation of endpoints generated by M's Gaussian center. For example, points in blue have a high expectation that they are generated by the blue Gaussian center, and the same for other colors. Then in maximize step, we assume the expectation is constant, then we will minimize objective function QP. Basically, this objective function QP represents the distance between P and the weighted average of the point cloud. Therefore, in M step, the Gaussian center will mainly move to the weighted average of the point cloud, as you can see from the animation. We will loop till the Gaussian center converges to a stable position. And just to note here, the noise of observation is taken into consideration, but the main idea of GMM process still holds. You can refer to the paper for detailed mathematics. However, simply using GMM is not enough, because motion in GMM could be arbitrary, while we would like to have coherent motion. Therefore, Schaumann introduced the CPD in the deformable object tracking. The idea of CPD is that every point motion should relate with other points. For example, if the third point has a velocity W3, the rational point will have the velocity in the same direction with an exponential coefficient in front. This coefficient will decrease with a higher geodesic distance. To formulate it in a mathematical language, P equals to previous P plus G times W, and G central will just be the exponential coefficient mentioned before, and W is the matrix of weight we want to compute. In addition, the regularization term is added to prohibit too large W. But CPD is not enough yet. CDCPD introduced the LLE regularization term. CPD could make sure that the local coherence from one timestamp to the next timestamp. However, in long term, the motion could still be not coherent. So to calculate LLE regularization term, first, one point kth nearest labors will be chosen. For example, if we choose 4 nearest labor for P4, those black points will be chosen. Then LLE algorithm tells us how to calculate L use the initial configuration, where every entry inside L is a linear weight between ith point and jth point. For example, P4 is expected to be close to P2 times L42 plus P3 times L43 and so on. The regularization term here requires every point at any timestamp stay close to the linear combination of its k nearest labors. However, these regularization terms are not enough yet. The image shows the results when tracking the rope with its edge covered for CTCPD. From the left image to right image, there is a large shrinkage because the right rope tip disappeared. And it's obviously not true in real life. And we are inspired by Kalman filter, using the model prediction to improve tracking results. We introduced P-prediction here, which is a prediction result based on models in these papers. The regularization term we added here is a distance from P-prediction. Basically, it will penalize too large deviation from prediction results. After GMM, we added posterior constraints. We formulated it as an optimization problem. The objective function is the distance from GMM results, and the optimization is subject to the following constraints. The first is long correspondences introduced in CDCPD. The idea is assigning long grid position to corresponding points in P. And the second is limiting the distance between two connected points within lambda times of the initial geodesic distance. And just to recap here, rho ij is the geodesic distance in the initial configuration, and lambda is a hyperparameter in our algorithm. In addition to these two constraints introduced in CDCPD, we also added self-intersection constraints. And at first, we select two edges, EI and EJ, from edge set E and regard them as two line segments. Then, we calculate the shortest distance Sij and corresponding nearest points. One thing to note here is that the calculation is based on the previous object configuration. Then we could find two corresponding nearest points in the current configuration. And P near I minus P near J is the right red vector shown here. and the unit vector along previous P near I minus P near J is the left red vector shown here. And we require their dot product should be larger than S if Sij is smaller than Scheck, and S could represent the width of cloth or radius of rope. To deal with obstacle interaction, we also added obstacle interaction constraints. First, we will find corresponding nearest points OM and normal vector NM corresponding to the nth point on previous configuration. Then we will just constrain the nth point on the current configuration stays in the same side of the obstacle as shown in the red area shown here. And in summary, this is a convex optimization problem, and we solve it using Groby package. To evaluate our performance on significant occlusions, we tested rope edge covering, where one edge of the rope will be covered by the obstacle, as you can see in the right first image. And for obstacle interaction, we tested rope interaction and cloth interaction, as you can see from right two images. And for self-intersection, we tested lifting crossed rope and cloth folding, as shown in right two images. And here is the specific parameters when running experiments. Note that we choose color segments, mentation, and primitive shapes for simplicity. For the prediction model selection, we tested each of the following three models. The first one is no motion model, which basically predicts there is no motion movement. And the second one is diminishing rigidity model, which maps the motion of grippers to the motion of deformable objects using Jacobian approximated. And our demonstration of this idea is shown in the image below. If the gripper moves towards one direction, the deformable object will move accordingly with different displacements. And the third one is constrained directional diminishing rigidity model, which takes the obstacle and gripper motion direction into consideration. In the simulation environment, we first tested the rope edge covering as shown in the video. At the beginning, our method is slightly better. When the edge is covered, CD-CPD and CPD plus fix results will shrink to visible parts, which lead to larger error later, as shown in the right image. We then tested the cloth interacting with the cylinder as shown in the video. Our method won't penetrate the cylinder and have a higher accuracy. For the physical data, we have a similar rope edge covering test, which have similar results as shown in the simulated data. For rope cylinder interaction, our method will not penetrate the cylinder and is accurate. And similarly, our cloth cylinder interaction test can still stay outside of the cylinder and is accurate. We tested self-intersection case on rope by lifting across the rope. Our method and CPD plus 6 won't penetrate rope itself, while CD-CPD will. For the cloth folding, our method could show a distinguished layer structure, while CD-CPD couldn't. In conclusion, we contribute by proposing a regularization term to handle significant occlusion and two posterior constraints to handle obstacle interaction and self-intersection. And thanks for your attention.